Okay, section 1.1, real numbers. Our objective is going to be to operate with real numbers and understand closure properties in the real number system. So before we can operate and understand this real number system, we need to know what the real number system is. So we're going to go ahead and we're going to start in this list at the very bottom with this definition of whole numbers. Our whole numbers include the counting numbers. So the numbers we use to count with, the counting numbers, and 0. Okay, and I like to think of this on a number line. It's the place where the dashes are. So here would be 0, 1, 2, 3. It doesn't include no of the in-betweens. No, what I call the in-between numbers. So for example, it's not going to include the number in between 0 and 1, with like 0.5. It's not going to include that. Or any of the numbers in between 2 and 3, like 2 1/3, 2 1/2, 2 1/4. It's just 2, it's just 3. So up here on this diagram, when I'm talking about the whole numbers, we're talking about the number 0, then comma 1, 2, 3, 4, etc. So I'm going to write dot, 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 showing that goes on forever. But there is a smallest whole number. The smallest whole number is 0. Okay, so those are our whole numbers. Okay, so those are our nice round whole numbers that are, we use them to count, we use them on the number line. Those are our whole numbers. Okay, the next is we're going to go into the integers. The integers are the set of whole numbers. So basically, all of these whole numbers are also in this integer group. So the whole numbers and their opposites. Okay, so 1 is in the integer group, hence why this whole number bubble is inside the integer bubble, but also -1. -1 is an integer, but not a whole number, because it's the opposite. Also -2, -500, -8, okay? So the integers, then we have all our whole numbers, and then the integers then include all those negatives. So integers have those negative numbers. Okay, so you might be asking, well, hey, what's a rational number? You remember we said these down here had no in-betweens? The rational numbers is where we then include those in-betweens. So a rational number is any number, if it can be written as A over B. So basically, when I think of rational number, I think of fraction. But it can be written as a fraction, A over B, but where A and B have to be integers. A and B are integers. And I know, we skipped this rational number idea. We skipped this irrational number idea, but it's easier to talk about rational first and then go to irrational. Okay, so our rational numbers can be written as a fraction. So all of these integers that we talked about here can be written as a fraction. Like -2 can be written as -2 over 1. 3 can be written as 3 over 1. They all can be written as fractions. So if you can write it as a fraction, then that makes it rational. So for example, 2/3 is a rational number. 1/5 is a rational number. -3.6 is a rational number because it can be written as -3 6/10. Which would then be 36/10, which then, again, so we're doing I can divide those both by 2, and I get 18 over 5, -18 over 5, don't lose that negative. Again, all of these are equivalent, but I can write -3.6 as a fraction, okay? Okay, whereas there's some numbers that cannot be written as a fraction. So basically, irrational numbers cannot be written as A over B. Cannot. So irrational, I like to think as not rational. And you might be wondering, what numbers are those? Okay, so one of the most famous irrational numbers is the number pi. It's a non-ending. Usually they tend to be non-ending, non-repeating decimals. because the repeating decimal can be written as a fraction. So if it's a repeating decimal, you can write it as a fraction. For example, 2.5, but the 5 repeats. So like 2.5555. That can be written as a fraction. Okay, we should have done some practice of that in middle school, and we'll review it again later on this year. Other irrational numbers are square root and cube root of non-perfect squares. For example, the square root of 2. If you were to type that in your calculator, the square root of 2, it's looking what number times itself is 2. It's not a nice number. Okay, it ends up getting a non-ending, non-repeating decimal, whereas the square root of 25 is rational. And actually the square root of number 25 is a whole number because it can be simplified down to 5. Okay, so we probably should eliminate it from here and put it there in that whole number list. Okay, but the cube root of 10. Okay. If you don't remember cube root, we are gonna work on those a bit. That's a number times itself 3 times. For example, the cube root with a little 3 there of 8 is a whole number because that's actually 2. Because 2 times 2 times 2 times 2 is 8. Okay, so a bit of review there. Okay, and now we put these two numbers together and we get a real number. So a real number is basically any point on the number line. Okay, so it includes all our rational and irrational numbers. So it's the rational and irrational. Okay, so the rational and irrational numbers make up that real numbers. Yes, there are some numbers that are not real. Okay, and go figure, we call them imaginary because they're not real. We'll learn about those later in a couple years. It's not quite an Algebra 1 content. Okay, so there we have the definition for all our real numbers, but every real number is either rational or irrational. Okay, there are no numbers that don't fit into one category or the other. Basically, to distinguish between the two is, can you write it as a fraction? If you're not sure if you can, check to see, is it a non-ending, non-repeating decimal? Okay, so first of all, the square root of 5. So use the definition of rational and irrational numbers to justify each statement. So here we're saying the square root of 5 is an irrational number. Since 5 is not a perfect square, 5 is not a perfect square, meaning I can't get to it by multiplying a number by itself. So it's irrational. So it's not a perfect square, so cannot be written as A over B. Hence, that's what makes it irrational. Okay, 5 is not a perfect square, so it cannot be written as A over B. If we go ahead and look at a calculator and type in the square root of 5, we get 2.23606797775. You can tell there's no like repeating pattern there. So it's a non-ending. It doesn't actually end there. This is just the rounded version of it. It's a non-ending, non-repeating decimal. So that's what makes it irrational. -5 is a rational number. Yes, it can be written, didn't leave enough room for this, as -5 over 1. There, right there, makes it a rational number, since it can be written as the division of two integers, -5 and 1. C, 5.26262626 is a rational number. Yes, it is a repeating decimal. So it can be written as a fraction. Okay. If you're really wanting to know, it's 521 over 99. Okay. If I take 521 and divide it by 99, I get 5.26262626. If you notice Desmos here, this puts a 3 at the end. That's just rounding because there's a 6 after. It's just a round. Okay, so yes, it is a repeating decimal, which makes it rational. Okay, so now your turn. Pause the video and do this problem. Okay, now that you're done with that your turn problem, we need to talk about something called closure. Closure over here. A set of numbers is said to be closed or to have closure under a given operation if the result of the operation on any two numbers in the set is also in the set. Meaning, okay, if I add a whole number to another whole number, any whole number, if I add a whole number 8 and add it to another whole number 10, I'm going to get a whole number. Okay. If I add two numbers on the number line, it's going to give me another number on the number line. So we say that the whole numbers are closed over addition. Okay. Integers, again, that's a positives and a negatives, are closed under addition, subtraction, and multiplication. Because here, when I add two integers, I also get an integer, right? This is going to give me, if we remember, that's going to give me negative 70. Okay. If I subtract, and okay, this negative 70 is also an integer. That's what makes it closed. Integer, integer plus integer equals integer, always. So that makes it closed. It's a lot harder to prove closure than to prove not closure. And we're going to look at how to prove one or the other. Okay, so here another one, subtraction. If I take an integer, subtract another integer, negative 2 minus a negative 5, if you remember, this would be negative 2, then plus the opposite of negative 5, which is 5. So that gives us 3. Again, also an integer. Integer minus integer is integer. And again, if I multiply, also an integer. So they're closed under addition, subtraction, and multiplication, but not under division. If I take negative 24 and divide it by 14, that doesn't go in evenly, so I don't get an integer. I get the fraction negative 24 over 14, which simplifies, let's see, divide by 2, negative 12 over 7. Not an integer, hence not closed. Okay, negative 15 over 6. So 15 over negative 6. I can divide that by 3. That gives me negative 5 halves. Again, not an integer, hence why it's not closed under division. Okay, so what about rational numbers? Are rational numbers closed under addition? Okay, so rational, again, fraction. So if I take 1/2 and add 2/4, am I also going to get a rational number? Okay, well, if you remember, I need a common denominator, so this would become 2/4 plus 2/4. Well, looky there. Okay, that gives me 4/4, which is 1 whole, which is also a rational number, 1 over 1. Okay, 1/3 plus 2/8. Okay, I would need a common denominator. Okay, I could keep listing rational, rational, and rational until I get one that works, until I get one that doesn't work, but I'd be listing for a while. So to prove closure, a lot of times you have to use what's called a general case, meaning if I have a fraction, a over b, and I want to add some random fraction, c over d. Again, a, b, c, and d could be anything. First off, I need a common denominator. So I'm going to multiply this first fraction, top and bottom, by d. And I'm going to multiply the second fraction, top and bottom, by b. So I have a times d over b times d plus c times b over b times d. So when I add them, I'm left with ad plus cb, ooh, a lot of letters, over common denominator of bd. Okay, so here I am multiplying two integers, which we know is closed, multiplying two more integers, which we know is closed. We set it up here, multiplication of integers is closed. And then we're also adding them, which also closed. Okay, because again, remember a, d, b, and c are integers. That's by definition of rational number. That's the definition of rational number here. They're integers. Okay. And then I'm dividing it by b times d, which also is integer. So I have integer divided by integer, hence it is rational. So I've just proved closure. Okay. You will not be asked to do a proof like this on your practice. I just wanted to kind of show you. This is actually a proof of closure for the addition of rational numbers. Okay, I won't ask you to do a proof of closure. Again, that might not be super intuitive to a lot of you, okay, which is fine. We'll get there. Okay, the next one, are irrational numbers closed under addition? So meaning if I add two irrational numbers, like the square root of 3 plus pi, okay, so this is a non-ending, non-repeating decimal plus another non-ending, non-repeating decimal. Yep, I'm going to get, I can't actually put these together. I would just end up getting the square root of 3 plus pi. Like they're not like terms or anything. Like I can't do anything with them to put them together. But I do get irrational. Now, is that always the case? Okay. I don't know. Okay. So what I'm going to do is we could list a bunch of different other irrational numbers. I'm going to do some, and you'll see there, one thing is if you're trying to prove closure, one thing to look at is always opposites. If I take pi and add negative pi, they're opposites. What do I get? I get 0. I don't know why I made it a no. I get a 0, which 0 is rational because I can write it as 0 over 1. So an irrational plus an irrational got me a rational. So they are not closed. And I would have got that. Oh, that looks like dosed. I would have got that no matter which opposites I would have picked. Okay, and what we found here is a counterexample. A counterexample is one specific example that proves a statement false. Okay. So it's really easy to prove something false. All you need is one example that it doesn't work for. It's a lot harder to prove something true because then you need to prove all possibilities are true. Okay, so it's much easier to prove something false. Okay, so now I want you to go ahead and pause the video and do your turn number 2. When is the sum of two irrational numbers rational? And I would encourage you, look for some counter examples there. Okay. All right, now that we know what closure is, here is a sweet little graph that shows us when I'm looking at the rational numbers, it's closed under all its operations, meaning if I add rationals, I get rational. If I subtract them, multiply and divide them, I'll always get rationals, whereas irrational is not closed under any of them. So we like to work with rational numbers. The real numbers are also closed under all the operations. Okay, so a real number, whether it's rational or irrational, when you add, subtract, multiply, or divide them, you'll always get real numbers, which obviously, because we don't know about unreal ones yet. Okay, so here we need to, given that 2 is irrational, so the number 2 is, the number 2 is rational, square root of 2 is irrational. We want to classify each number described as either rational or irrational. Justify your answer. So here I'm adding a rational number to an irrational number. What am I going to get? Okay. Well, first off, I can't put these together. They're not like terms. So I just end up with 2 root 2, okay, which we can get a decimal approximation for it if we want to. 2 plus the square root of 2. There I get a long, crazy decimal, which is probably a pretty good indication that it's going to be irrational. Again, I can't put anything together. Same with me subtracting. Irrational minus irrational. Again, I can't put anything together here, so that makes it also irrational. Okay, the next one. Here I have 2 times the square root of 2 plus the square root of 2. Okay, so I'm adding, so I have 2 times root 2. I'm adding another root 2 to it. So I'm going to come in and I'm going to think of this. This is 1 root 2, and this is actually 2 of them. So I have 2 of them plus 1 more. So using like terms, I've got 3 root 2's, which again, that's a times. So I have 3 times root 2. But since root 2 is irrational, so is this whole thing. Okay. It's irrational because of the square root 2. And really, for justify your answer, I could say on all of these, they are non-ending, non-repeating decimals. Okay, but we could also look at that closure idea. The irrational numbers are not closed. We can't guarantee it there. Okay, and this next one, we have 2. I'm going to kind of split this guy up. We've got 2 times root 2, and I'm going to write it this way. This over 1. Okay, so if I multiply straight across, I get 2 root 2 here and then 2 on the bottom, which gives me back to the beginning. Okay, but then now what I can do is I can look at just this guy. That gives me 1. 1 times root 2, which is just root 2. So hence that also makes it irrational. Non-ending, non-repeating a decimal. Okay. So next ones. To prove that a statement is false, you only need to find one counterexample. We talked about that previously. Determine whether each statement is true or false. If false, give a counterexample. So irrational numbers are closed under addition. Well, if you notice we went back here, are irrational numbers closed under addition? Well, no, because we said pi plus negative pi is 0. We can use that same counterexample. So we would say false, since pi plus negative pi is 0, and 0 is rational. Okay. The sum of a rational and irrational number is a rational number. Well, up here, again, we don't have to reinvent the wheel. Rational plus irrational here got me an irrational, so that would make this statement false as well. False. 2 plus the square root of 2 is irrational. Irrational numbers are closed under division. Well, I'm going to go back to our most famous irrational number, pi. If I take pi and divide it by itself, how many times does pi go into pi? Once. And 1 is rational. Hence, it is not closed under division. I just need to find one example. Now, if I would have used square root of 2 divided by pi, that is irrational. Okay, but that's not what I used. I used pi over pi. Again, counterexample, you just need to find one. The sum of a rational and an irrational number is a real number. Well, first of all, the rational numbers are real numbers. Irrational numbers are also real numbers. Again, these are all real numbers. If we go back to here, real numbers is the heading on all of them. Real numbers can be divided into 2 categories, rational and irrational, but they're still real. So basically, in this one, I'm looking at a real number. Sum means plus. A real number plus a real number. Real numbers are closed under addition. So this would be true, since real numbers are closed under addition. Since real numbers are closed under addition. Okay, last your turn. What is another closure statement that you can disprove by giving a counterexample?